Welcome, everyone. Good morning. I hope all of you had a great extended weekend. I know you didn't have any assignments for today. Do you have any questions or problems from before that you'd like to work through? All right, well, then we'll get started. Please note that the contact info is up there in case you want to send a question, or you've got the chat that you can use. Any one of those will work. I think today's lesson is going to be pretty short. We're going to be going through lesson 1.5, which is about inverse functions. All right. So the goal today, as you can tell in the objective here, find inverse functions informally, and then we're going to be able to verify that two functions. How do we prove that two functions are inverses of each other? And then we're going to use the graphs of functions. By looking at the graphs, we should be able to also tell whether they're inverses or not. And then we're going to be able to use something called the horizontal line test to tell if functions are one-to-one. And then how do we find inverses using algebra? Those are the goals we're going to be aiming for today. So from the alternate website, we're going to use some of the things there to go through this. So we have a function here. We're going to be looking at 2x plus 4. It's shown, let's see. Yeah, it's shown right here, and it's shown here too. An inverse of a function literally undoes the action of a function. If f of 2 is 3, then f inverse of 3 is 2. Notice that ordered pair is literally inverted. Every function has an inverse, but not every inverse will be a function. So we can always find an inverse, and that's what I'm interested in, being able to find the inverse. And then we will note, is the inverse a function or not? So here we go. We've got this function, 2x plus 4. Remove the f of x and write it as a y, and then literally swap the x and the y. So x equals 2y plus 4, and then go about the algebra of solving for y, the new y. So we would subtract 4 from both sides, and then we would divide both sides by 2, and we come up with 1/2 x minus 2. That is the inverse of the function f. Yeah, here's, I guess, the same example. Let's do another one. Let's pull this off, and let's take and find the inverse. The first step is swap. And then solve for the new y. So add 7 to both sides. Divide both sides by 3. And there is your inverse. This -1 exponent is sometimes used to represent inverse. It actually, what? -1 power actually means reciprocal. And that's not always a perfect match, but that is the notation used for an inverse. Okay. So let's head back over here. All right. So if you're going to prove that one function is inverse of another, you need to compose the function, the original function, with its inverse. So if we do f of f inverse, we should come up with an x. So here, in place of the x for f, we're going to plug in this new 1/2 x minus 2. So 2 times x plus 2 times our new x, 1/2 x minus 2, plus 4. And you can see that really does come out to x. All right, you can also do it in reverse. And in fact, you should be able to do it in reverse. Let's do f inverse of f of x. So now we're going to plug in 2x plus 4 in place of the x in the f inverse over here. Over here on the right. Whoops, got to get my pen. Over here on the right. So in place of that x, we are now going to plug in 2x plus 4. 1/2 times 2x plus 4 minus 2. And again, it comes out to x. So, in fact, you should remember that when you take an inverse, when you find the inverse of a function, they will not normally be the same. Not at all. In fact, the only time they will come out the same is when they're inverses of each other. And then they both will come out to x. So tomorrow on the assignment, if you're asked to demonstrate or prove that one function is an inverse of the other, you need to do this composition, f of f inverse of x, to demonstrate it. Okay, here we have a quadratic example. So the quadratic, this time the function is x squared minus 3x plus 9/4, way at the top there. So once again, we set the g of x, we call that a y. And now I'm going to pull, in this case, right here, I'm from that step to that step, I pulled a step called completing the square. So let me just show you. I want to just demonstrate this to you a little bit. Let's just take, well, I guess I could do this on the next function, but let's just take one here. Let's say we have, for the function, y equals x squared minus 3x plus 2. All right, so we swap the variables. In place of x, you put a y, and in place of all x, in place of all in the y, you have to replace an x. Now, how are we going to solve this for y? We could use the quadratic, or we could use a technique called completing the square. So what you do when you complete the square is put the two y terms, leave a little space, move the plus 2 over. Now what you want to do is take half of this guy. Half of 3 is 3/2, and 3/2 squared is 9/4. That's the perfect number that will make that into a perfect square. So this now will be a perfect square trinomial. Of course, I can't just willy-nilly add 9/4. So to make it legal, and I know this seems completely insane, we're going to subtract 9/4. So we've added it, we've subtracted it. Now, here's the reason we did that. This is now can be written as a square, and 8/4 is 2. 8/4 minus 9/4 is a negative 1/4. So now it was very important to me to write that as a square. And by the way you can tell it's y minus 3/2 is it's either the square root of the 9/4 on the end, or it's half of the middle term. It's both. Then in the next step, add the 1/4 to both sides, and then take both square roots, plus or minus square root x plus 1/4, and then lastly add 3/2 to both sides. And we have basically found what y is equal to. Now, so anyway, that's the technique called completing the square. I'll just keep that in view here for a few more seconds. If some of you are possibly, I don't know, you may not remember that, or you might not have used that for a long time. So I'm just going to pause a few seconds if you want to take note on that. So now I'm going to return to the problem we were looking at. So this really is, I mean, this already was a perfect square here, because half of 3 is 3/2, and that really is the square root of the last term. So, but now we have a problem, and the problem is that notice we got a G inverse equals plus or minus the square root of x plus 3/2. And the inverse is no longer a function. It's an inverse, but it's not a function. And the reason it's not a function is because of this guy right here. That plus or minus. So you've got here, let's just take a look at it. So we've got, let's take a look at Desmos. And I just got to look back here. What did we have? So we have x squared minus 3x plus 9/4. So that's basically our beginning function. And then I'm just going to throw in the identity function. And then what we came up with down here on the bottom, negative plus or minus the square root of x plus 3/2. So square root of x, and then, I don't know, my memory is pretty bad here, plus 3/2. All right. And you'll see that we have just the top, and then when we do the minus, we've got the bottom half, and if you look, we do have a nice mirror imaging going on with respect to the blue identity line. But you notice something here about this, okay? The red curve, the one we started off with, x squared minus 3x plus 9/4, is a function. It passes the vertical line test. Okay. When we looked at the green, that is a function. When we took the other part, the plus and the minus, then this thing over here fails the vertical line test. So the inverse is no longer a function, but it's still it's an inverse, and that's important. The book kind of goes a little bit berserk on this. They call a function, like they say this red function here is not 1-to-1, meaning when you rotate it 90 degrees, it's not a function. So we'll talk more about that as we move on. So the cool thing happens here. When you plot a function, I've already indicated that to you, but when you plot a function and its inverse on the same set of axes, you get this mirror imaging. So the black line, that is 2x plus 4. The 1/2 x minus 2 that we figured out, that's the yellow line. And you notice if you put the identity function on here in green, y equals x, it becomes the perfect mirror line if you look at it for those two functions. So an inverse is always the mirror image of its original function with respect to the identity function. Here you can see it with the quadratic that we did. Yeah, we already took a look at this a few minutes ago. You've got the red is the original, the yellow is the positive square root, the blue is the negative square root, and I mean you can see that. So in the book they speak of this. You can run the horizontal line test on the original function, and you can see that it fails, which means that when you rotate it, it's not going to be a function because it'll fail the vertical line test. So this horizontal line test is for telling if an inverse really is a function. Okay. When you're trying to make inverses, here is just some notation. If a function has, you plug in a 2 and out comes a 3, we say the ordered pair is when you plug in a 2, out comes a 3, 2 comma 3, and f inverse of 3 is 2. That is, the ordered pair is now literally reversed. So in an inverse, everything gets flipped around. G of 7 is 100, G inverse of 100 is 7. The ordered pairs literally get turned around backwards. Here's kind of an interesting example. Let's find the inverse of y equals negative x plus 6. So we would first swap the variables, plug in an x for y and a y in place of x, and solve for the new y. So we would subtract 6 from both sides, and then we would divide both sides by -1. And it turns out this crazy thing is its own inverse. So at the bottom here, I mean, this is a rare case. Whenever you have a negative x, it's going to be its own inverse. So you can see that if we plot it here, you can see it's its own mirror image. Okay, that's kind of unusual. I thought I'd point it out. So I'm going to repeat this again. We've already had this, but let's just say we start with the blue function x squared. Nice parabola. All right. You can see that when I find the inverse of this, we're going to wind up with this plus and minus square root, this red thing here, and that is not going to be, so this function, this blue function is not one-to-one. That is, it fails the horizontal line test. Meaning when you find its inverse, you can see it fails the vertical line. So here's a case. So one-to-one functions are examples when you find the inverse, where the inverse will not be a function. So let's just talk about this one a little bit. Number 31. And the directions here, let's just take a look. Number 31. Number 31, it says, find the inverse function of f, graph them on the same set of coordinate axes, and describe the relationship between the graphs and state the domains and ranges. Okay, so f of x equals the square root of x. So we write y in there in place. We switch the coordinates. We solve for the new y, so in order to get the y out from under there, we'd have to square both sides, and we come up with this being the inverse. So let's just take a look at that in Desmos. Okay. So we've got the square root of x, the square root of x, which looks like that, and we found its inverse was x squared. And you notice they're not mirror images of each. You know, what's the domain of this purple guy? This purple guy, the domain is just what? X is 0 and positive. But what's the range? Only positive. Flip them around. What's the domain of this one? All reals. So you see how the domain has changed? And so just be aware of that. It's the odd thing that what happens when you solve an algebra problem by taking the square of both sides, it kind of hides the sine root. And even though it's an inverse, it does create this not totally matching situation. And that's what the book was getting at there. Number 65. Let's just take a look at this one. Okay, I'll take a look at the directions here. Number 65. So 65 says, take this function x cubed plus 2x plus 1 and find its inverse, find f inverse of a. So in other words, when the answer to this thing is a, what's x? So if we come back to the problem, and you find out you can't find the inverse, take a look over here and you'll see what I mean. Over here on the right. Here's the original. If you just swap the variables, you get x equals y cubed plus 2y minus 1. And well, no matter what you do, you can't solve for y. I mean, you could get it, you could factor the y out like I did here, but you can't get y by itself on one side. So at least with the techniques I've shown you so far, you can't do it. But you could still do the problem, because if the answer is 2, and just by playing around, you can find out that x would be 1. You know, just try it. 1 cubed is 1, plus 2 times 1 is 2. 3 minus 1 is 2. 1 works. So you're going to have, you might have a couple problems. So here's a case. Do we only complete the square when the equation is a quadratic? Claire, sorry. I didn't see your question until just now. I know that was 10 minutes ago. Yes. Now, you can also, besides using completing the square, we could have used the quadratic. But there are times when completing the square is handier. Okay, let's see, inverse example. Oh yeah, so now let's take a look at this problem. So again, I've got a quadratic here. We start off with y equals x squared minus 8x plus 1. X equals y, so now I just swapped the x and the y in the second line. And can you tell what I did here? I used completing the square. I took the 16 and I'm here. Let's just do it off to the side. Negative x, negative 8 y. Here, let me just write this down. Y squared minus 8y plus, and then we have plus 1. Okay, so let's go off to the side. So we've got y squared minus 8y plus 1. All right. And what, I forgot, what was that equal to? Let's find out. It was equal to y. It was equal to x. Okay, so split the plus 1 off to the right so you have a little more space. And then find half of this, 4. 4 squared is 16. That's the perfect number that will make this into a perfect square. Of course, I just added 16, so I have to subtract it. So now you'll find that this is literally y minus 4 squared, which is why I did that, and this is minus 15. And then when you add 15 to both sides, so this is that completing the square again. And then when you take both square roots, and then add 4 to both sides. Now, what I wanted to show you is, let's take a look at how that turned out. So that turns out, yeah, that's your inverse. And your inverse is these 2 square roots. So in the picture, the original is this orange graph, and the 2 square roots, here's the purple and then the black. And as you know, that inverse is not a function. Notice though, if you look at it, it perfectly matches. You can see that we have a nice symmetry in the problem. Okay. Another thing you may run into in this problem set is something that goes like this. All right, it says in exercises 101 to 106, use the figure to write the expression in algebraic form, given y equals arc cosine of x. So what that means is when you take the cosine of y, you're going to get x. So when you take the cosine of this angle right here, you're going to take what? Adjacent over hypotenuse, and that is x over 1. Okay. Well, given that information, what's going to happen? I mean, what's the Pythagorean theorem here? You've got one leg squared plus the other leg, which I don't know, I'm going to just call square at the moment, squared, equals the hypotenuse squared. And box squared equals 1 minus x squared. And box, which is this thing over here, this side, this leg, and you get this. So if we write that down, now on the diagram, now you can answer these questions like number 102. What's the sine of y? The sine of y is opposite over adjacent. So that would be, how about 103? What's the tangent of y? I'm sorry, I said opposite over adjacent. I meant opposite over hypotenuse. And because it's over 1, I didn't do anything. The tangent is what? Opposite over adjacent. So that would be square root 1 minus x squared all over x. So you really can do this the inverse trig functions. You know, our cosine just says if you take the cosine of y, you're going to get x. It's just this inverse way of saying the cosine, which is a trig function, and the arctangent is, you know, those are all reverse. So you're going to have some trig problems like that that will involve inverses. Okay, so that brings us down to here, 1.5. The assignment then includes what? Yeah, somebody in the other class asked me about this. When it says 1 to 7 odd, so 1, 3, 5, 7. 9 to 12, 9, 10, 11, 12. So, you know, 107 to 111 odd, 107, 109, 111. So, just an explanation there of what those mean. Okay, I've been doing all the talking. Questions? Claire, I'm sorry it took me so long to answer your question. I sometimes don't look over to the chat window. Okay, so we'll meet again tomorrow. This should be the assignment for tomorrow. All right, thank you. Have a good day.